Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, my wonderful students of Senior 1. I want to welcome you to this lesson, physics lesson for Senior 1. And as always, my name is Teacher JB, your physics teacher. And once again, we are going to be engaged for the next 30 minutes for our physics lesson, and I hope you are going to enjoy it. Now, today's lesson is still on Unit 4, and you can see me with a ball, a volleyball. Do you guys know this? Yes, I believe some of you know it. I do play it very many times. And so why we are having it here is because it is connected to Newton's second law of motion, which is our lesson title today. And at the end of this lesson, every one of you should be able to state Newton's second law of motion, and also you should be able to use the formula F equals ma. That is our main learning objective today. You should be able to state Newton's second law of motion and use the formula F equals ma. And also today we shall see that Newton's law of motion can be applied to sports that we normally do, like football or even volleyball. And that's why we have this volleyball. Okay. To begin with, I want to ask you a few questions about the units or topics that you must have learned before. And there are two words that I want you to remember. These words are, one, acceleration, and two, momentum. Do you remember those words before? You must have met them before. So we want to remind ourselves what acceleration is and what momentum is. Let's begin with acceleration. Do you remember what acceleration is? Think about it. Yes, acceleration is the rate of change of velocity. Isn't that true? I'm very sure we looked at that before. So today we just want to remind ourselves of the formula of how we can find acceleration of a body. So acceleration A is equal to V minus U out of what? Out of T, acceleration. Do you remember that formula? Try to remember that. A equals V minus U over T. And A is standing for acceleration. Just read along with me. V is standing for final velocity. U is standing for initial velocity, and T is standing for time. That is quite easy. We need to remember that formula because we are going to use it to understand Newton's second law of motion. Now, if you had forgotten, I'm going to have one demonstration here that I want you to see very well, which is going to help us to remember initial velocity, final velocity, and acceleration. So I have made a makeshift runway, a curved runway, and I have marbles, okay? They are spherical and very smooth, so they will move along the surface. So I'm going to raise my runway so that it acts as an inclined plane. The idea here is we want to see the difference between initial velocity and final velocity. And also, we shall also look at acceleration after we have seen this illustration. Okay, let's demonstrate. So what I'm going to do, I'm going to call this point A. And the other point right there where it enters the beaker, you see that? I'm going to call it end B. So what I want you to observe is the speed of the marble at this point A. Will it be the same as the speed of the marble at point B? That is what we want to look at. So watch carefully and see. So I'm going to release the marble. Do you see that? The speed of the marble at point A, is it the same as the speed of the marble at point B? The speed at A, is it less than the speed at B? Is it more than the speed at B? Let's demonstrate using a second marble again. So I'm releasing the marble. The velocity at this point is the initial velocity at point A. Do you see that? Let me repeat with the third marble. Do you see that? So the question is, the velocity at point A, is it the same as the velocity at point B? According to me, no. The velocity at point A is very small. The velocity at point B is higher because the body is moving faster when it is at point A. Now, simply because the velocity is increasing, the velocity of the marble was increasing, then we can say the marble was doing what? Was accelerating. So if we want to calculate acceleration, it is v minus u over t. I hope that reminds you of what you learned before. Then the second idea is on momentum. Momentum, again, try to remember what it means. Momentum. Momentum is a quantity of a body which is in motion. And it is given as a product of mass and velocity. Remember, if you don't want to use velocity, you can also use speed. So the product of mass and velocity of a body is called momentum. So it means momentum, and we use letter small p, is equal to, product means we shall multiply. So it is mass times velocity. So it means P is equal to m times what? Times v. And also remember velocity, we have initial velocity and final velocity. Instead of giving it like this, you can also say momentum is equal to m times what? Times u. This is initial momentum, this is final momentum. Initial momentum of the marble, if you remember our demonstration, is the momentum of the marble at this point. Final momentum is momentum of the marble at point B. Okay. So why we have been reminding ourselves about these concepts is because we are going to need it in Newton's second law of motion. So let us state Newton's second law of motion together. And I would love that you read it along with me, okay? If you read it, you'll remember. You need to read and practice it many times, then you can remember. And as I told you last time, you don't cram physics. Try to understand it. You don't cram it. For now, we shall repeat these words, but we shall expect that you can change them into your own words. You can use different words, not necessarily what I've written there, as long as they mean the same thing. Okay, let's read Newton's second law of motion together. Are you ready? For me, I'm very ready. Good. What does it say? The rate of change of momentum, do you see? We talked about momentum, now we are seeing it here. The rate of change of momentum, it's right here, is directly proportional to the applied force, and it takes place in the direction of the what? Of the force. That is what Newton's second law of motion tells us. We are going to read it one more time. The rate of change of momentum is directly proportional to the applied force, and it takes place in the direction of the force. That is what the second law says. And so we want to use this second law to derive this formula, F equals ma. We shall also tell what F, M, and A are. That's what we shall do. Okay, let's go ahead. On this chart, I have got a small car. Everybody knows a car, right? For a car to move, a force must be applied. So the force is applied to a car at point A so that the car begins to move as it goes towards point B. Does it take time for a car to move from A to B? Does it? Yes, it does. You can measure the time. And so, the rate of change of momentum is directly proportional to the applied force. Let us look at change of momentum. Now, when you're looking at change in momentum, we need to consider momentum at point A and momentum at point what? At point B. Which one is initial momentum? Initial momentum is the momentum that we get at point A. So momentum at A is going to be, look, remember the formula for momentum, mass times velocity. So this is going to be mass of the car times velocity. Remember the velocity at point A is what? Is u. Let's look at momentum at point B. Momentum at point B is going to be mass, which is m, times what? Is it u again? No. Times v. Okay? They're telling us rate of change. Before we look at rate, let us look at change of momentum. So, change of momentum is going to be, just like we looked at change in velocity, final velocity minus initial what? Velocity. So change in momentum is going to be final momentum, which is mv, minus initial momentum, which is what? mu. So that is change in momentum. Let us now factor in this rate of change. So rate of change. I'm going to change the color of the pen, my marker. Let me use red. So rate of change of momentum. So what is going to be the rate of change of momentum? Rate means we divide it by time. So we shall look at change in momentum, which is mv minus mu out of what? Out of time. The time taken from here to there. Let's go ahead. So this rate of change of momentum is mv minus mu over t. But what are they telling us? They are saying the rate of change of momentum is directly proportional to the what? The force. Directly proportional to the force. So we shall have F is proportional to, I hope you remember, that is the proportionality sign. Proportional to M, but also here you see M is common, so I can put V minus U, then over T. Are you comfortable with this? Just factorizing M. That's what we have done. And so this is going to be F is equal to, if I remove the proportionality sign, I'm going to introduce a what? A constant K. You have seen that before. Then we shall multiply this by M, then into V minus U out of T. Okay? This T is under V minus U. Okay, let's go back. Did we talk about V minus U over T? It's right here. So V minus U over T is equal to what? Is equal to A, which is acceleration. So it means F is equal to K times M, then times what? Times A. Good. So, if we make K the subject, try to make K the subject, okay? If we make K the subject, I hope you remember it, K will be equal to, I divide this side by MA. So it is going to be F out of MA, that is K. So if I apply a force, assume I have applied a force of 1 Newton on a body whose mass is 1 kilogram. That force will produce an acceleration of 1 meter per second squared. So these ones will cancel out each other. So we shall find that the value of K will be equal to 1. So if K is equal to 1, our equation then becomes F is equal to K, but remember it is 1. Do we need to write 1? No, because it doesn't affect anything. So we shall remain with M times what? Times A. Have you seen that beautiful formula? I'm going to surround it so that you can be able to see it very well. I'm going to surround it with black. F is equal to MA. F equals MA. And F stands for friction? No. Food? No, of course. F stands for force. M stands for mass, the mass of the body we are talking about. Like here, mass of the car. And A stands for what? Acceleration. The rate at which the velocity of this car is changing when a force is applied. And that is a very important formula that we wanted to derive today. And so please remember it. I also have a wonderful flashcard here for you to help you remember this formula. Do you guys remember the magic triangle? Here I have F, then MA. I hope you know how to use it. Force is equal to mass times acceleration. If I want to get acceleration, you know what I'm going to do? I'll say acceleration is equal to force over mass. This is divided by this line you are seeing here. And here there is multiplication. If I want to get mass, mass is equal to force divided by acceleration. Do you see that in your ones? You need to remember this formula because you're going to be using it for a very long period of time, for as long as you are studying physics. Very important formula. So mass is force over over acceleration, sorry. Mass is force over acceleration. Acceleration is force over mass. And force is mass times acceleration. Also, this can be useful to you. Distance is speed times time. Do you remember that? This is density, the symbol for density, rho. So density is mass over volume. It's not the topic we are looking at today, but a magic triangle is a beautiful way for you to remember your formula. So keep that in mind. All right. Since we have derived this formula, we can now go ahead and state Newton's second law of motion in another way. And the other way is, let's read that together also. Okay? The second statement. They all mean the same thing. You can state it this way, or you can state it in this way. Or you can even have other sets of words. As long as they mean the same thing, no problem. So let's read this together. Are you ready? Good. The acceleration of a body is directly proportional to the force. Directly proportional to the force means the acceleration increases with the force. The bigger the force on a body, the bigger the acceleration. But indirectly proportional to its mass. You think about that. We are going to read it one more time. Okay? The acceleration of a body is directly proportional to the force, but indirectly proportional to its mass. So what does that statement mean? We are going to have another demonstration here. And in this demonstration, we have two balls, volleyball and a softball. This is lighter, this is heavier. So small mass, and this one is a bigger mass. I'm going to put these balls on the floor, and I will give them the same amount of force and see what the effect of this force is on the two balls. Are you ready for that? If you have your ball at home, you can also demonstrate this. So I'm going to put them down here and this. And I'm going to give them a small force, but same force. I know how to kick a ball. I hope you guys know how to kick a ball as well. So I'm going to begin with the big ball, big mass. So that is the force I've given it. Have you seen the way it has moved? It has accelerated because the velocity has changed. I'm going to give the same force to the small mass. Have you seen where it has moved? It has moved very far. And yet I applied the same force. So what does it mean? It means if you apply a force on a mass, that mass will accelerate. But if the mass is small, the acceleration will be more. The body will move faster. If I apply a mass on a big body, it may move, but it may not move very fast. Look at our illustrations here. You have a big bus, and then there's a small car. Do they have the same masses? No. So if we give them the same force, that is the car and the bus, same force, do you think they will move at the same rate? They will accelerate at the same rate? Okay, let's find it out. Using our formula. Do you remember our formula? F equals ma. So here, the force is 60,000 newtons, and the mass is 30,000 kilograms. A bus is very heavy. So what we want to do is we want to get acceleration. So using F is equal to ma. Acceleration is going to be equal to F over m. Do you remember that from our magic triangle? So the acceleration is going to be the force, which is 60,000 newtons, divided by the mass, which is 30,000 kilograms. And so these three zeros will cross out. Even this one will cross out, by the way. And by 3, this is going to be 1. By 3, there is what? Is 2. So it means our acceleration is going to be 2. You can even use newtons per kilogram, no problem. Or we can use meters per second squared. That is the acceleration of the bus. Okay? Let us also find the acceleration of the car. So using the same formula, acceleration is going to be F over m. Okay? And so this is going to be the force, which is 60,000 divided by mass. And what is the mass? The mass is 5,000 kilograms. Of course, a car is lighter than a what? A bus. Not so? Lighter. Again, the 3 zeros will cross out those 3 zeros. This will be 1. What do you multiply by 5 to get 60? If you check very well, you will find 12. So acceleration is going to be 12. meters per second squared. Okay. That's very beautiful. Now, let's look at this. Did we not give them the same forces? Yes, we gave them the same forces. But which one created more acceleration? The more acceleration was created on the car. Imagine 12 meters per second squared, but the bus only 2 meters per second squared. So the bus will move at a smaller acceleration compared to the car. And that explains this statement of Newton's second law. For the same mass, for the same force, there will be more acceleration on the smaller mass, and there will be less acceleration on the bigger mass. Very good. So as we summarize, we should remember the main concepts of our lesson today. And also check yourself and see that we have met our learning objective. Our learning objective was you should be able to state Newton's second law of motion. Are you able to state Newton's second law of motion? Yes. Either using this or that. They mean the same thing. 2, we should be able to apply the formula F equals ma. Can we apply the formula F equals ma? I think yes, because it is right there. Okay? This is how we applied it. And so, during your free time, especially at the end of this TV lesson, I will leave you with some assignment that you are going to do. But before we go to the assignment, you might be asking yourself, is this applicable in real life? Is it even linked to other subjects that we study? Yes. If you go to chemistry, you are going to be looking at the movement of free electrons, maybe in a vacuum, and that also you require the idea of the mass of the electron and the force that is applied to the electron, maybe by a magnetic field, and we see how fast that electron can accelerate. And that idea is used in lots of areas, including in TV screens. If you study like physics, you look at how the electrons are used to produce images on a screen, using pretty much the same idea. You must be able to know how the electron or the atom accelerates in a magnetic field. And if you go to engineering, when you are designing cars, let's say for racing cars have a smaller mass compared to cars like buses. So that, because in a racing car, you want the car to move so fast and become the fast. Okay? So it should be having a smaller mass, not as big as a bus, so that when you give it a force, then the racing car can accelerate very fast, so that it can perhaps be the first in the race. So that is briefly how this idea, this concept of Newton's second law is applied in other subjects, but also in real life. There are so many other applications. Make sure you go to the Physics for Rwanda Schools, that book, which is also found on the REB website. Then you can read more about Newton's second law. You can also use the internet if you have access to the internet. So I want to thank you so much, my students of Senior 1, for being good listeners, good viewers, and I hope you have been taking your notes. I want to wish you a good time, and I will see you next time. Bye-bye.